Yeah, hello everyone. We warmly welcome you to the next episode of Fraunhofer IPMS webinar session. My name is Andreas Hatzemann and I'm working at the business development and I want to be the moderator for today. Today Jan Graman is joining our webinar session. He is head of business unit active optical systems at our institute. This business unit is focusing on research and development of 1D and 2D electrostatic driven MEMS scanner for different applications. Today we want to focus on the LiDAR application. We want to take a closer look at reliability and durability of MEMS scanner and if they can be considered as solid-state LiDAR. A few words before we start. The presentation, the slides will take around 20 minutes. During the webinar, you can contact us by using the chat function and/or send us your question. After the presentation, we will have some time to take a closer look at these questions. The slides and webinar will be provided after the webinar to you via email. And so this should be enough from my side, so we can switch to Jan Graman and his presentation, and yeah, enjoy the presentation.
Okay, well, thank you for the introduction. Hello to everyone. For the further webinar, I will turn off the camera so that you can see completely or concentrate on the actual presentation. And as already said, it's today about MEMS mirrors, and for many applications they can be used, but LiDAR is one of the really upcoming important applications for MEMS scanners. And the question always is it a solid state LiDAR or not? So solid state actually means you don't have any moving parts, and apparently, since it is a mechanical oscillating MEMS mirrors, you do have oscillating parts, so moving parts. And the question is, does that play a role or doesn't it? So at the end, it's not so important are there really no moving parts, but really important is, are these MEMS scanners potentially shock and vibration resistant enough in order to be used for LiDAR applications? And if that is the case, of course, they also work for other mobile applications where the requirements are much lower, at least as well. Okay, before going specifically onto the MEMS scanning mirrors and its properties concerning vibration and shock, I just want to very shortly on 2 slides show you what we do here in the Institute. So here at the first slide, you see that we do research and feasibility studies very typically for different customers, and we do design and process development, usually really following a feasibility study. We go up to demonstrator and prototype level of our hardware, so our chips, also our electronic, depending on if our customers want to have an electronics driver, for example, or a packaging so that we can send chips packaged in modules, for example. So we go up to demonstrator and prototype level, and we can go beyond that up to pilot fabrication. So above all, for small medium enterprises who usually do not have the access to foundries or have millions of chips needed for their applications, but just a few 10, a few hundred, sometimes a few thousand, we try to fill the gap, and our pilot fabrication scenario allows us to deliver qualified components for product introductions of our customers. And last, we also offered to transfer our technologies to foundries, for example, in case that the number of chips needed exceeds our fabrication capacitance, for example, or if we cannot produce it cost effective enough for our customers. So those are typical reasons to do a transfer to a foundry. Right now, we just had a conversion from 6-inch to 8-inch wafers. So we have a complete MEMS clean room facility with 8-inch, and we have another clean room at the Institute for 12-inch with the CNT. Okay, so what are the technologies? So we are in surface micromachining, for example, which you can see here on the left side. So a typical example are here spatial light modulators. We do fabricate in our clean room. Then we are working on active silicon. So for example, an ion sensitive so-called ISFET for the measurement of the pH values. Then we have MEMS on CMOS. So we do, for example, use CMOS wafers and then build up our MEMS devices on these wafers. And the fourth one, which is also the technology that leads to the more specific points for the scanning micromirrors here on the left side, it's bulk micromachining. So here we do use typically a silicon device layer of BSOI, so a buried silicon oxide insulator to etch directly into the device layer and therefore define our MEMS function. And that can be seen, for example, here with these comp structures, which we use as drive for our scanning mirrors. So that brings me to the functional principle of electrostatic MEMS scanners, because that is what we at least mainly develop here on that bulk micromachining technology. We also are into magnetic and have a few piezoelectric activities, but our main focus are electrostatic MEMS scanners, and that for a pretty good reason, which you will see later on throughout the webinar. Up here in the left side, you see an example of a 2D resonant scanning mirror. So you have the actual mirror plate here in the middle. That's an SEA image. So that's why you see the gray color here. And you have comp structures around it in order to drive that mirror. And on the other hand, you see that deflected other axis of the mirror orthogonal to the first one. And that is the mirror plate in order to get a 2D actuation. These mirrors can only oscillate at a fixed frequency that can be tuned a little bit, but in order to achieve a certain amplitude, you want to fix it at the design frequency, and that is in that case 27.6 kilohertz for that inner side mirror and 100 hertz for the outside plate. The whole thing is operated in atmosphere, and here on that picture you can see how it is driven. So the electrode comps are in plane, as you see here, and then you apply a rectangular voltage as seen here, and the mirror plate is driven towards the rest position. You always have a little bit asymmetric fabrication. A few nanometers are enough there in order to get an oscillation started. And you turn off the electrostatic voltage in rest position so that the mirror can be driven through by its inertia forces. And then you have to get the right point again at the maximum amplitude at the mirror, and you turn on the voltage again. That way you have the most efficient drive for these electrostatic scanners. Down here, you see just technology used in order to make a 2D mirror. So these red lines here represent insulation trenches that are needed in order to have a mechanical stability throughout the mirror plate. So the pendant practically is here seen on the left side, for example. So that's mechanically stable, but at the same time, it insulates in between the silicon device layer that determines the thickness of the scanner. And that allows us to make 2D scanning mirrors. Here on the right side, you see another example for the options of that technology. So we cannot just have mirrors that rotate around 1 or 2 axes. We can also have a translational movement. So that's a 5mm mirror that moves up and down. In this case, we can only do that in vacuum because the air damping is really much higher than with a torsional oscillating scanner. And that specific mirror here can do a stroke, so plus minus 500 microns, so a complete stroke up to 1 millimeter, and is driven at 500 hertz. So those are possibilities for the resonant scanner technology. Then down here, we basically have an extension of that technology towards a quasi-static one. Quasi-static in this case means we can drive the mirror not just at a certain frequency, scan frequency that has to be basically sinusoidal, but we can also drive it in a triangular mode. We can drive it to a certain position and hold it there. So that means we have a quasi-static actuation of that mirror. And in order to achieve this, we do need an offset between the 2 comp electrodes. So up here, you see that they are in plane. So in order to get a quasi-static actuation, one of the electrodes has to be out of plane. And this is shown down here. And the concept to do this is actuated on the slide as you see it now. So we have a top wafer with a stem that is bonded to the actual device wafer with the scanning mirror, and it deflects via certain actuation pads an offset between the 2 comp electrodes. And this stays stable over time and allows us then to do a quasi-static actuation as seen here. So for the outer axis, we can have here a linear movement, for example. And for the inner axis, we can have a resonant movement so that you have a linear movement in vertical direction, for example, and a sinusoidal movement of the scanner in horizontal direction. Another possibility that this quasi-static actuation enables is shown here. So for example, we can vary the line width in such a 2D scanner by adjusting the speed of the scan trajectory of the quasi-static axis, which is shown. So you got it faster here, so you have a larger line width, and you can drive it slower here, and the line width by constant oscillation of the resonant axis becomes more narrow or more tight. All right. Now I go one back. I have to mention that these mirrors, due to the bulk micromachining technology, are made out of single crystal silicon, which is a quite important property for us, because that single crystal silicon allows us to not have to look at fatigue of the mirror, for example. So we don't have any fatigue. And most important for us concerning destruction is the vibrational and the shock load onto the mirrors, which is of course not allowed to break any of these structures as shown here. And therefore we do make shock tests, and we use a setup shown here at the left side that allows us, with a ballistic principle and a pressure of 4 bar, to accelerate a metal block with the device under test. And on this metal block, which is shown down here, there are different scanner chips, or one scanner type, for example, is stick to that metal block, and we can then look into different directions in X, Y, and Z and test how the pulse shape, the shock really damages or not damages the scanning mirrors. So we do have an acceleration sensor that measures the pulse we apply to these scanners, and the whole test is conducted according to a MIL standard that's military and space US standard. So here you see a typical example. So we can, for example, apply over 5,000 G to these devices, and the typical pulse width is 0.33 milliseconds. And that pulse width has to be withstanded basically by the scanner chips, and we increase it from 1,000, 2,000, 3,000, and so on towards higher pulses in order to determine when do the chips eventually break, and that with different designs. And there I brought you an example today on the right side. So here we used that resonant 2D scanner. I showed you the slide before, and one specific characteristic of that scanner is that it just has 100 Hertz resonance frequency on the slow axis, which means that this is a quite soft spring used for the mirror. And what you can also see here is that our standard is that our designs, unless our customer wants to have something else, at least has to withstand 2,500 G of pulse height and a pulse width of 0.7 milliseconds. And now looking at that graph, you can notice that this quite soft scanner was well beyond these 2,500 G, actually going up to 3,500 G, where you have the first 10% of device under tests failing. And then, of course, with increasing pulses, increased pulses, more and more devices start to fail. Yeah, that's one important point, how we test our scanners, and where we can see that they can, even for soft springs used for these scanners, can withstand quite high pulses. And of course, there's also always a possibility to increase even that pulse, that shock resistance, by using a suitable package. Okay, that brings me to vibration measurements, another important point. But before going a little bit more detailed into the question of vibration and how we measure it, is the question, yeah, how can you do that in operation of a scanner? Because you of course do want to know how does the scanner behave on one hand destructively concerning vibrations, on the other hand, is your trajectory, so your scan line, is somehow affected by vibrations during operation of the scanner. And here it helps us a lot that we have a piezo resistive sensor in order to detect the position of the scanner, also in the two axes. And that example is brought for a scanner here that is quasi-static on this axis and resonant on this one. And below you see a graph that shows that we achieved here about 9.5 degrees deflection plus minus, meaning 9.5 times 4 degrees field of view for that quasi-static axis, and 17 degrees on the resonant axis, which also has to be multiplied by 4 for the field of view. So that piezoresistive sensor is located quite near the actual anchoring of the torsional springs, and is classically, as known from pressure sensors, does change the resistance with the stress, respectively strain, it sees from the movement of the scanner. That is read out by a Wheatstone bridge for the scanner. And here on the right side, you can see a few results. So for triangular trajectory, in this case of the quasi-static axis, we achieved in closed loop So using the sensor signal in order to drive the quasi-static scanner more precisely in its trajectory, in order to minimize the error between the actual linear trajectory and the deviation seen. So in these two graphs below here, you see the deviation, and there we have two parts of it. One is an error in the linear region. That means this error shown here is systematically. So for each scan of that triangular trajectory, you will have the same deviation of the linearity. So it is reproducible, and you can basically, depending on the application, compensate it. And that is in the range of 14 millidegrees error for that scanner. It is always also design dependent. And then below we have the standard deviation. That means that basically it represents the noise which is not reproducible for each scan trajectory and cannot be compensated. So there we are in the range of 2 millidegree. So let's say with a signal to noise ratio at least of 3, you want to have here 6 millidegrees for the actual signal. So that brings us to the point that we can use that piezoresistive sensor in a test setup in order to detect how the mirror moves during operation and their vibrational influences, which without that integrated position sensor would be quite a challenge, because somehow you would have to do it optically, and at the same time that setup would have to be resistant to the actual vibration put on the measurement setup. So we clarified how we will be able to measure the actual influence of vibration. Now on that slide, I want to show a little more specific what does actually is influenced by vibration, or how do the scanner characteristics have to look like in order to respond to a environmental vibration. And therefore I put two designs down here, one very soft with a scan frequency of 127 Hertz. To be more precise, it does not necessarily have to be the scan frequency. So when we talk about a quasi-static mirror like this one, that is the first resonant frequency, which you usually want to avoid for the actual scanning. And then you have further frequencies that do represent eigenmodes of that mechanical system shown here on the left side. And these mode shapes, so how the scanner oscillates parasitically dependent on these frequency or connected to these frequencies, is shown here below. And that is of course also true for the design 2, but here the difference is that the first resonance frequency is quite a bit higher, so at about 509 Hertz, and also the other frequencies then parasitic frequencies go up in frequency. So that means each of these parasitic modes I can, by intention, excite by using a sinusoidal excitation. So when I use a vibration setup and have a certain sinusoidal frequency starting to drive the scanners, then they would react quite strongly when that sinusoidal frequency hits the here shown frequencies. That is one point. So you can measure that way how strong the mirror reacts to these parasitic modes in resonance. Another possibility or additional setup actually is to use the power spectral density of vibration noise. So this way it is more realistic for the disturbance in operation, because usually you won't have an exciting frequency that is driving the mirror resonantly, but you will have frequency, let's say, flashes or spikes that show up and then vanish again, or you have a certain noise that excites the mirror. And there, the power spectral density is more realistic, which I will show in a minute. So just for understanding, not each of these shapes here, these mode shapes, is really critical. But for the vibration, the following, or the other way around, for the shock, the following modes can be quite important. So that is this mode. So here, basically, the scanner makes a movement into Y direction. That is also shown here by the coordinate system. So in direction of the comp electrodes. And as you can see here, there's only a certain space, and that could, for example, destroy the scanner if the movement is too large. Another one is that that mode shape. So in Z direction, which means the mirror plate moves up and down, which you also don't want to have. And that could, for example, break torsional springs for the scanner. And another one shown here, that's basically a mode where the scanner is turned around its Z-axis, and therefore you get, again, a movement of these comp electrodes towards the other electrode and these comp electrodes towards here, which could also be damaging. So you definitely want to avoid these modes. Respectively, they should be not excited to a degree where they can damage the scanner. That is one point to look at. The second one is what are modes that could actually influence the trajectory precision that I showed on the slide before. And here it is the case that, of course, that is our used torsional direction of the scanner. So if we have a deviation here, that's something we don't want to see in the scan line. And also a movement in Z direction can actually lead to deviations in the torsional deflection. So that's, let's say, is the theoretical, roughly the theoretical basis. Now, how do we have tested? So we used standards for vibration reliability testing, and there are all kinds of different standards out there. For example, for agricultural machinery, for automotive destructive vibration, US military, the MIL standards are already mentioned, or semiconductor vibration loads, and all these have different power spectral densities for the acceleration used, as you can see here in that graph. So you've got the frequency down here in logarithmic scale and the actual power spectral density that is applied to the device, or has to be applied to the devices on that axis. So we used here an automotive destructive vibration test, primarily to see how it affects the scanner in operation. So it is basically a worst case that we use here in order to determine that characteristic. And you can see that this red line here has a quite high power spectral density in between 100 and, well, 3 to 100 hertz, and then drops down by 200 hertz and further to higher frequencies up to 2 kilohertz. So we calibrated our measurement setup, and what you see here is the reference of that standard I just showed you in yellow, and the blue line is the actual measurement by an acceleration sensor of the vibration of the power spectral density we applied to the devices. And there you have, of course, a certain noise. The mode back here has nothing to do with scanners, because here we did not even use a scanner on the setup yet. That is a mounting mode of the setup we use to put the scanners onto the vibration setup. Okay, and again, you see here the highest load is between 3 hertz and 200 hertz, because here you have the highest power spectral density for the devices. Okay, so what did we do? We did test the scanner too, according to that standard. and the scanners were not damaged. So we did not have any damage of the 2 scanners I showed you, and other ones we also tested. Secondly, we put these scanners onto a car in order to see how the actual power spectral density looks like for a real test scenario. And please don't wonder, because that looks a bit bulky here. It's just, we used it to have a functional test setup. It's not a miniaturized version. That was not the objective here. So we used our position sensors and accelerometers to, the integrated position sensors, again, to see how the scanner really moves and in what directions. And secondly, what is the actual load driving down a very bumpy road in Dresden. And here you've got the power spectral density. Here you've got in red the standard again as reference, which is used for the destructive testing. And the blue line is the power spectral density we measured driving down a very bumpy road, showing that there are 2 orders of magnitude between the actual test requirements and where we are in the range really using a car, having it mounted to basically the window here, so the car casing. So that is the road we used for that. So you can just see the different bumps, and we just drove it by 50-60 kilometers per hour. So and you can see here on the right side, according also to the power spectral density before, how the actual acceleration levels looked like in X, Y, and Z direction. And you can see that they are really much lower. So by a factor of at least 10, partly to up to 100, compared to the actual standard for testing. So in that means to sum up the results, having used these different vibration loads, is first of all, the vibration sensitivity of MEM scanners is determined by their eigenfrequencies, which you can influence within the design. Secondly, the vibration load used for the destructive test from the automotive standard LV124, we have seen no damage to the IPMS MEM scanners, even for the low frequencies I showed to you with just 127 Hertz of eigenfrequency. The next point is that I showed you that the Z direction and vertical direction and the lateral Y direction are the most critical ones concerning an operation influence. And there we've seen, based on the destructive test, that below 500 Hertz, you have to look a little more closely concerning operation influence. Beyond 500 Hertz, you basically have no problem, and 2 kilohertz, you don't even have to look at operation influence on the scanners. So the other point is, when you are in the range of below 500 Hertz, we saw that via closed loop control for these quasi-static axes, we can improve the vibration resistance of the scanner significantly. But all these points here are valid for the LV124. So compared to what we actually saw on the road, where the test requirements are, or where the vibration load is much lower than we actually expected, it shows that there's no influence even on the softer scanners around 100 Hertz at all, because the acceleration levels are much lower than our used destructive test. So that means for LiDAR application, first of all, we can go to quite large mirror apertures, because usually a larger mirror aperture means the spring has to be a bit softer, or the whole eigenfrequency becomes softer because lower because of the larger mass. And secondly, we can go to quite large deflection angles so that we can well achieve 60 degrees field of view for a 5mm scanner, which could be quite interesting parameters for a LiDAR application. The other point is that this means when you, for example, go to a design that has parasitic frequencies in between 500 to 2 kilohertz, and you design it well, you can basically consider the scanner as solid state. So because you just don't see any vibration influence, it's definitely not damaged, and you won't see a deviation in operation of the scanner. So that brings me to my conclusion. So I've showed you we've got tilting and translational mirrors in 1D and 2D deflection. We can do that resonantly and quasi-static. We went so far up to optical scanning range, so field of view to 136 degrees, which is a very soft mirror then, and 1D, of course. We have frequencies in between 0 hertz to up to 100 kilohertz realized in different designs. We have typical mirror diameters in the range of 0.5 to 5 millimeters. We have sometimes larger ones. It's always very specific then, project specific, but that's a range where you can, let's say, very well design MEMS scanners and also be cost effective concerning chip size and so on for a later product. Additionally, the planarity is an important thing I did not elaborate on today, but we always looked at the deformation of the mirror plates in movement is low enough so that there's no influence on the actual reflected laser spots mostly. We can provide high reflective coatings. We do have a position sensor integrated on chip. We have an excellent long-term behavior due to the technology used. So the single crystal silicon, there's no fatigue, which means on the other hand that we can also withstand high temperature resistance. So up to 200 degrees Celsius. And we can do the whole thing in a qualified way in order to go to prototypes or pilot fabrication. And I showed you today that there are really vibration and shock resistant even for soft designs. And yeah, with that sentence, I want to end and thank you for your attention.
So Jan, also thanks for your time highlighting the MEMS scanner technology and sharing your experience with us. Now we have some time for some questions. Of course, you can send us after the webinar. You can send us your questions to me or to Jan, and we will reply to it. Currently, we have 2 questions. The first one, Jan, is about our test scenario, or your test scenario on the bumpy road. The question is, if you mount the MEMS at the front of the car, which is closer to the engine, the vibration will be more served. Did we try it, or do we have any experience about this when we install the MEMS scanner on the engine, closer to the engine?
Mm-hmm. Okay, yeah, good question. We have not yet tried it, so these were first results. I might expect also different acceleration loads at different places when we mount the scanner at different places in the car. That's definitely the case. But one thing to point out here again is when you look at my slide again at the acceleration levels, even when we have two times or 2.5, 3 times the acceleration level shown here, because fixing it to the front window, which I would not expect. I would expect it to be more but lower than what I just said. This has no significance really compared to the vibrational load we applied with the LV 124 standard. So yeah, that's something that could be done, but I would not expect any influence on the mirror because we are so low in the acceleration level.
Okay, thanks. The second question is about what is the radius of curvature requirement? Do you have achieved large radius of curvature, also von der Krümmung?
Yeah, that is actually customer dependent. So we have a standard value where we say that our mirrors have to at least achieve a static curvature of larger than 5 meters. We are typically in the range between 8 to 12, 15 meters of static curvature, but we can adapt that specifically if our customers need a certain static curvature, because it depends mainly on the applied reflective coating we use for the mirror. So, and there's always a possibility of optimization if that is needed for a certain customer application.
Okay, thanks. Now we receive some more questions. The next one regarding the piezo resistors for position sensing. Don't they need to be temperature calibrated in order to compensate temp effects? Is there any temp diode integrated?
Exactly, very good question. Yes, we had to temperature calibrate the piezoresistive sensors before doing the testing I showed here today to you. And let's say we don't have an extra temperature sensor on chip. In this case, we did it by a setup we have here in the lab to do the temperature calibration. But basically, we have the possibility also to measure the temperature using on-chip structures, which we have not done yet. So we've shown it in the lab, but we have not used it in a real application scenario.
Okay, great, thanks. The next one is, what is the deflection angle achievable? I think this is focusing on the maximum deflection angle, which is possible.
Yeah, that is a question that is hard to be answered because that really depends strongly on all the different characteristics of the scanner. So how large does the mirror plate have to be? What frequencies have to be changed, either as oscillating frequency for a resonance scanner or a scan frequency quasi-statically, meaning you need high eigenfrequencies, and all these different things has to be looked in order to determine the final field of view, and that's something, or deflection angle of the scanner, and that's something if we don't know from the parameter requirements of our customers, if we can do that, then we usually offer a feasibility study where we use all our design know-how in order to see can we achieve a design that is, of course, that can also be fabricated and achieve a certain deflection angle. So that might not be a very clear answer to you. Therefore, I can tell you, like shown on that slide here. Here we had a scanner that had, I think that was about 200 hertz. So, and with such a 200 hertz scanner, it was somewhere in the range of 1 to 2 millimeter. We achieved these 136 degrees. So basically 44 degrees plus minus deflection angle of the scanner. But typical deflection angles for applications we try to serve our customers with are deflection angles where we are in the range of plus minus 5 up to plus minus 15, sometimes plus minus 20 degree.
Good, thanks, Jan. The next question is about the temperature range requirement. What is the temperature range requirement? Can the mirrors meet the temperature requirement of the in the automotive sector?
The simple answer is yes, they can. The more a more detailed answer is that the scanner chip is here actually not the problem, because due to the characteristics I told you about, single crystal silicon, we don't have any metal lines going over torsional springs and so on. We therefore no fatigue. Therefore, it's no problem to come to a qualified chip based on that technology. The more interesting thing here to look at is the combination of the used package for that scanner to integrate it into a product that goes into a car, because the interchange between the package and the scanner, that does not necessarily destroy the scanner, but that can of course lead to different mechanical stresses that are applied onto the chip, and that can influence, for example, a drift of resonance frequency and some other characteristics. So here you really have to look at the package, which is also an expertise from us, to really design a package according to the application in order to prevent their influence by temperature, for example, or being able to compensate for the temperature influence.
Good, thanks, Jan. Jan, then we go directly to the next question. Do your MEMS mirror operate in linear regime? What if large angles of rotations are required? There, of course, non-linearities arise. How do you deal with non-linearities?
Yeah, the point is, maybe I go back on my slides a little bit. Here on the right side, you see, in this case, a triangular trajectory was chosen. So we wanted to have a linear scan here for that blue, for the time of the blue line, and here again for the backboard scanning. And of course, you do see linearities here at top. So these, in this case, are not used for the actual, let's say, projection or imaging application. So and we tried by a closed loop regime to drive the scanner as linear as possible within that range or for different trajectories. So now you have to know that, as you can basically see here, for that quasi-static axis, you see here a drive voltage and a deflection angle. And just the correlation between deflection angle and drive voltage already is not linear. So we compensate for non-linearity by a certain drive scheme, and then the correction by closed loop control in order to keep the scanner linear.
Good, thanks. And so I think we will come to the last question. Which resonant frequency is possible with a 5mm mirror with decently low dynamic deformation?
Well, here I cannot say that by heart, basically. So it would be good when I have a few parameters, for example, maybe after the webinar sent, so that I can give you a more qualified answer. Because let's say the influence on the dynamic deformation is correlated to about the diameter of the mirror, which you gave me, 5mm, to the power of 5. The frequency also goes in there strongly to the power of 2, and the deflection angle goes into that to the power, of 1. so linearly. So the question is, I would need to see, let's say, these parameters all together in order to tell you where probably the dynamic deformation for our technology will be.
Yeah, maybe later on we can go in detail, or when we receive the question one more, we can reply in more detail. One more question we received: can non-linearity compensate in resonance mode in contrast to static mode?
Sorry, but could you please repeat the question?
No problem. Can non-linearity compensate in resonance mode in contrast to static mode? So if we have any idea to compensate between in resonant drive mode or in static drive mode, or is it just non-linearity always the same?
Okay. So when I understand the question properly, it says, how can I compensate the nonlinearity in either resonance scanners or in quasi-static scanners?
Exactly. These are two parts.
Yeah. So the first, or let's say the second part, the quasi-static scanners, I try to explain that we have a nonlinearity within the scanner due to the deflection of voltage curve anyway. And these come, for example, from the mechanical structures we use and also from the electrostatic drive. So it always introduces a certain nonlinearity, which we compensate by the used drive voltage for these scanners. And then we measure the position where they really are and use that position feedback in order to have a quite complicated algorithm to control the scanner trajectory more precisely. For the resonant axis, that's different. For a resonant scanner, you basically have an approximate sinusoidal motion, which you cannot compensate for. So you have a sinusoidal motion, and each sinusoidal trajectory has a certain linear part, but it's of course smaller than what we can do with a quasi-static scanner. And if you want to use a resonance scanner and you need a linear trajectory, then you have to stick basically to the linear part the sinusoidal trajectory gives you. Because in the resonance scanners, you use the resonance frequency in order to have large deflections, even for high frequency scanners. Like I said, we go up to 100 kilohertz. So we have 50 and 100 kilohertz scanners that can do 5 to 7 degrees mechanical deflection. And that is only possible in atmosphere when you have a high quality factor. And that means on one hand, you have a high drive efficiency. And secondly, it means you can basically not influence the actual trajectory. What you can influence of the scanner is the amplitude. So you can, for example, use the position sensor and have a closed loop control in order to drive a resonance scanner that you have a constant amplitude, independent of environmental influences. But the trajectory is basically fixed.
So then, thanks, Jan. This was the last question. If any questions arise after the webinar, please feel free to contact one of us, especially me. In our next webinar on 19th of November, Michael Wagner, Head of Business Unit Spatial Light Modulators in our institute, will talk about the SLM technology in general and share his experience with you or with us. So finally, thanks once more for joining us today, and hope to welcome you at the next webinar session in November.
Okay, bye-bye. Thank you very much.
Bye all together. Bye. Have a nice day.